This is a numerical calculation for um, of a spring. We have here is L is 0.1, which is that's the length of the spring. K is 15, which is the spring at its relaxed state. The holder, we give it we make it a shape of a box, give it a position, and give it a size as a vector. The ball, we make it a sphere and give it a position, a radius, the color, and we make a trail equal true so that whenever the ball goes around, it makes a trail. The spring is in the shape of a cylinder. It gives it a position, an axis, and a radius. The ball, you give it a mass, you give it a velocity of a vector. Velocity is a vector, gravity is a vector. You give it a vector of negative gravity. You give it a time and the change in time. And your x is equal. The x is actually not needed. And then for down here, while time is less than 10, so this gives you like a time limit for how long it lasts at a rate of 100. L is the length of the spring, so the change, like the second length of the spring, it's the ball, the position of the ball to the position of the holder. And so you updated your length. F, the forces of the spring, is equal to negative K, because it's the negative force of the spring at rest, times ball, the position of the ball. And then right here, you're going to give it an acceleration so that the ball moves, and that's the sum of the forces over the mass of the ball. And then you give the velocity of the ball. You're going to update the velocity, which is velocity of the ball plus acceleration times delta t. And then you're going to update the position of the ball. So now it gives it a new position of the position of the ball plus velocity of the ball times delta t. And then your spring on the axis of the spring, it's from the position of the ball to position of the holder, and t is equal to t plus delta t, change in time, so the total time, and that is how it comes out.